Hey, everybody. Welcome back. It's 12 after the hour, and I would like to introduce our panelists to start out. And in addition to our keynote speakers, Aurora and Nicholas, I'd like to introduce Alexey, Vikhlinin. If you can unmute and just say hello.
I did unmute myself. Yeah, hi everyone.
Hi. And then Rachel Somerville is here as well.
Hi, good to be here.
Hi, Rachel. Edmund Hodges-Kluck is here.
Hello.
Hi, Edmund. And Colin Hill.
Yep, hi, everybody.
Hi. Okay, so we are going to kick off our panel discussion, and I have been looking at the Slack. There's a lot of interesting discussion. I'm actually going to start with what Aurora suggested we might start with, and that is the kind of surprises that we can envision or that we might be able to imagine from X-ray observations that are coming online in the near term and long term. There's already been a few responses to the thread that I started on this. Two that I think are interesting from Ben and Daniel are that accretion is hot in the present day universe, and the other one is all hot gas is out of equilibrium. This is from Daniel Wang. What do people think of these predictions, and can we speculate about others that might surprise us even more? I don't know. It kind of seems like accretion being hot isn't. I'm not that surprised by that, but maybe I'm surprised. Why should I be surprised? And panelists can feel free to just jump in, and if any participants have something to say, you can raise your hand.
I absolutely love the comment by Daniel. That's amazing. And, you know, I didn't have time, but I was sort of, a little devil was on my shoulder telling me to open this can of worms, and I decided not to do it. But the fact of the matter is, you know, all of these things we are modeling as a fluid, you know, and we worry about magnetic fields and we worry about cosmic rays, but we don't worry, for instance, about something like you have a fully dissociated electron ion plasma, okay? And it's perfectly possible that, for instance, if there's a shock going through, that the temperature of the electrons is completely different than the temperature of the ions. And in these very low density things, that stays this way for gigayears, tens of gigayears even. So is it okay that we are modeling this as a fluid? And I think the answer is nature is kind to us, and the magnetic field equilibrates electrons and ions, and it's probably kind of not a terrible approximation. But in certain situations, so I don't think it's going to turn out that it's non-equilibrium everywhere, and that's good. But it will turn out that it's non-equilibrium somewhere, and the question is, where are we going to find this? And I'm really looking forward to that.
What about accretion being hot? What do people think about that?
So maybe I'll jump in there. So the classic picture that we've all been learning for the last 20 years is that for low mass galaxies, galaxies lower than the mass of the Milky Way, that a lot of the accretion is cold, right, through these cold filaments. But I think that Greg Bryan showed some results from recent work by Viraj Pandya analyzing the Fire 2 simulations, in which that is not the case. So you can see the filaments in the dark matter, but the gas that is accreting into the galaxy is mostly hot. And that's due to the strong stellar feedback in those simulations. So I think it's a very interesting proposition that maybe this whole picture of cold accretion that we've all been, you know, sort of taking on board, that may not hold up in the face of these feedback models.
Ben, do you want to say anything about that?
I'm going to leave it open for the panel and everyone here to discuss. I think it's quite different than the high redshift universe, is all I'll say.
Edmund?
I guess, I mean, I don't know exactly what we will learn about hot accretion in the next, 5 or 10 years that is going to be completely ironclad, where it's no longer debatable, like, what is the most important thing. But I think that we could be surprised in either direction. I mean, we could learn that hot gas is ubiquitous and slowly cooling and is going to be important for the next 10 billion years, but that right now it has very little impact on the galaxy. We could learn that outflows, while spectacular, do very little to suppress star formation in galaxies. And conversely, we could learn that they're extremely important. Right now, like as if we go back to week 2, or week 3, I forget which one was non-thermal, I guess that was week 3. Right now the jury is very much out on the role of cosmic rays. And I think we're going to learn in the next decade just how important cosmic rays are. And there's going to be ways to tell that both from the SZ as well as from the X-rays, in addition to radio and other multi-wavelength observations. And so it could be that our current view of the hot CGM is, okay, it's massive, therefore it is important, could be overturned and into something where it's like it's massive, but it's not that important, or it's not as massive as we thought, but it's extremely important. The other thing, going back to what Daniel said, I mean, it could be yes that hot gas is all out of equilibrium, but going back to something I mentioned in the PRISM talk yesterday, the state of our knowledge about what the temperature and pressure of the hot gas is in a direct way, other than from the SZ, is not very good. And that's because at CCD resolution, most of the temperatures that have been measured around other galaxies, you can fit pretty much any galaxy with the same 2-temperature model. And that model is not physical. It represents some balance of hot and cool gas, but it's really tracing it's a non-unique equilibrium point when fitting a 2-temperature model to a complex emission vector distribution. So, we may learn that the pressure of the hot gas is actually substantially different than what we think it is, especially close to the disk, within the next, 5 to 10 years. This is the type of thing that could indeed lead to surprises about how important the gas is, how the gas near the disk connects to the extended CGM.
So I wanted to relate this to one of the questions that I wanted to bring up, and that is, can we finally definitively answer the question of why star formation is inefficient in low mass galaxies? So, is it ejective feedback? Is it because stellar-driven winds are driving the ISM out of those galaxies? Is it because the stellar-driven winds are heating the CGM and preventing it from cooling? Or is it because the CGM is perhaps out of equilibrium and not cooling as efficiently as we might have thought? So I think, all of these possibilities have been discussed now. And I think, tying them into that sort of big question might be helpful, and thinking about ways that we can use the observations we've been discussing all week to really answer that question definitively. That would be great progress.
I love that idea. When you say low mass, what do you mean by low mass?
Anything in a halo less than 10 to the 11 solar masses or so. So not really extreme things, things less than the mass of the Milky Way-ish.
Yep. And so what are our prospects for actually, probing those halos and distinguishing between these different scenarios?
How far do you need to go in radius?
Pretty far out, but they're not very big.
So yeah, 2 times the virial radius of a 10 to the 11 halo, right? Like that's only like 200 kiloparsecs.
Or less even, yeah.
It's not going to happen in a mission, absolutely, ever. You need a mission that is going to fly outside of the Milky Way if you want to do that. Okay, because in terms of emission, the Milky Way foreground is already killing you at a virial radius of a 10 to the 12 halo. And it's irreducible. At that point, there is nothing you can do. There is no way you can improve your instrument. And so the only way you will ever be able to do this is in absorption. And I don't know if you remember my plot. All of the gratings that are being proposed are empty triangles. And so we need to push for one of these X-ray grating missions if you want to, to really do a good job in absorption. I really think you need to go for that. So
Awesome.
fingers crossed.
Agree.
It could be interesting stuff to be done at smaller radii as well, because I think right now we are in a situation where we almost have no data, on hot gas and on gas in those halos, on warm and hot gas in those halos, even on the small radios, right? So every time you bring up observational capabilities that are, orders of magnitude compared to the state, today you start learning new things. Maybe you will change direction. So, things like metal content of the outflows at relatively small radii can tell you a lot about the feedback modes, I suppose, right? And this is totally within the realm of, maybe not the very next generation of X-ray observatories, but definitely things like links.
Okay. A lot to look forward to, it sounds like. Or we could plan for, 200,000 years from now when our X-ray telescope leaves the Milky Way halo. Okay, so I'm gonna switch gears a little bit and move on to something that's generated a bit of a discussion. Ben, Mark, and I think Joe have some related comments about the thermal pressure and the temperature profiles that Nicholas showed in his talk, and in particular, the comparison with simulation predictions. So Ben, maybe you can clarify this discussion point a little bit, and then I would love for Mark and Joe to jump in and then hear from the panelists.
Sure. Well, I'm speculating here a little bit because it seems very, the Amodeo result shows that from the TSE thermal SE effect and the KSE combined, you can get the temperature, and the temperature looks very hot out at 2 to 4 RVR around 10 to the 13.5 solar mass group to Z of 0.6, and I know that TMG is too low compared to that, and I would guess that I haven't looked into this, but I would guess it's not the density, but it's the temperature that is too low, and I'm sure that Eagle is even with less bearing on lifting and clearing and heating probably is even lower. So I was kind of surprised by how high the temperature was out there, because I think of a declining. I think there's declining, it's the temperature of maybe you would expect for the virial temperature of these objects, but at 2 to 4 RVR, I would think that the temperature would be lower, a lot lower.
So, sorry. Just one thing to keep in mind is that, and Nick, correct me if he disagrees, but I think you should interpret those as sort of a cumulative temperature profile. So you're measuring some average of everything interior to that radius. So it's not like every point is independent. So that can kind of bias your intuition about what's going on.
Good point. Good.
But I agree with you. It's definitely surprising.
So what it's got me thinking about, when we do idealized simulations of AGN feedback with narrow jets, they can go out quite far. And we know from the heritage of radio jet observations is some of them, the radio lobes are way out there. And so in a cosmological simulation, unless you have really high resolution, it's hard to get the momentum flux necessary to drill out to high altitudes. And so, this is not a fully formed thought. But it's got me wondering whether thermalization of some of that jet energy happens at larger radii in reality than happens in cosmological simulations of the current day. Something to look into for sure.
But Mark, this is well outside the virial radius.
That's correct.
I think this is, much larger than where you see radio lobes, much larger scales.
Well, megaparsec, more than that?
Yes, more than a megaparsec, I think. Is that right, Nick? Colin?
Yeah, that's about right. Yeah.
Right. So
Radio lobes are usually at hundreds of
They're the
kiloparsecs, I think.
wide, but they're not a large fraction of the radio lobes.
right, but I guess the general point is the farther out the kinetic energy is when it thermalizes, the higher the entropy of the resulting gas. What happens to it after that, I don't know, but I'm scratching my head trying to figure out what makes things so hot at such a large distance. And thermalizing the feedback energy at large distances seems to be what's necessary. And I'm speculating about how that actually, why that wouldn't show up in a cosmological simulation at the current time.
What I was getting at with my question was how much of it is, is it a contribution from structure formation and shock heating in the large scale structure in the cores of filaments, for example. I mean, it seems like we have to cleanly separate these contributions in the experiment, right? Or what's the expected contribution, right?
Okay, Dashka has his hand up.
Yes, so regarding this point, one experience that we have is by looking at cluster outskirts and how SZ effect contributed from ICM versus the large scale filaments, is that once you go outside of several times the virial radius, even around the most massive clusters, there are significant contributions from the large scale filaments. They actually tend to have, they do have 10 to the 6 Kelvin gas typically. And so I could easily imagine that if you have a galaxies that are embedded within the cosmic web, which actually typically has the virial temperature, like the cosmic web itself has the virial temperature of 10 to the 6 Kelvin, you might get quite a bit of contribution from large scale structures. So when you actually stack galaxies that are sitting inside of those filaments, we have to be thinking carefully about whether you're getting contribution from CGM, like the dark matter within the virialized region of the halo, versus the large scale structure shock. So this is something that probably needs to be worked out. These physics are incorporated in the hydro simulations, and in principle, once you do that exercise of pulling out, are you measuring CGM, or are you measuring IGM, or are you measuring a mixture of those two? I think that changes the function radius away from the galactic center.
All right, Nir, you have your hand up.
Thanks. Yeah, so this is, I guess, just to strengthen the points that Joe and Daisuke just made, that in cosmological simulations, even out to high redshift above 3, we certainly see very hot gas, 10 to the 6 Kelvin gas forming due to large scale accretion shocks in the cosmic web. And people here have heard me mention the intra-pancake medium. So at high redshift, that gets very hot, 10 to 6 Kelvin and above, and the cosmic filaments as well. So I think Joe and Daisuke's point is well taken. It'd be interesting to disentangle the kind of large temperatures due to accretion shocks in other components of the cosmic web versus the more spherical accretion shocks that we're used to thinking of.
Interesting. All right, Mark. Something to add?
While we have license to speculate, one of the things that's on my mind is the difference between relativistic energy density and non-relativistic energy density. When you're kind of blowing out bubbles and they're expanding and rising, the power law of your polytrope matters as to how much energy density you then have far out, and so most cosmological simulations, I guess, it's all kind of thermal energy and not relativistic plasma. But does anybody have a feel for whether that is going to make a big difference? I'll take that as a no. But yes, as you include like a higher percentage of cosmic ray energy, things might turn out differently.
So Nir or Daisuke, do you have thoughts about why cosmological simulations might not be properly capturing the shock heating in these filaments? Is this a resolution problem? Is this a problem with modeling of stellar feedback in low mass galaxies that are in those filaments, or what is your thought?
I don't think it has anything to do with feedback, because a lot of this hot gas exists really far away from any galaxies. This is really deep IGM. The resolution issue is an interesting question. It's something we're actively looking at right now by looking at a series of these simulations of the same volume run with different like resolutions. I'm skeptical as to how much of the heating is resolution dependent. Of course, subsequently, the cooling out of that hot medium is very resolution dependent, and you can wind up with, similar to as we see in the simulations of the circumgalactic medium, whereas you increase the resolution, you precipitate out more cold gas. We seem to be seeing similar features in this intergalactic shock heated gas, but yeah, that's more to be seen, I guess.
Maybe one question I have is that maybe more for the Nick and Colin is how, like, when we actually do these stacking measurements out to very large radii, I wonder how much like projection effect, large scale structure projection effect can contribute to the SZ effect as you go to larger radii, and whether we have encompassed large enough volume that can, like, large scale filaments is kind of permeating everywhere throughout the cosmic volume, and have we considered all of the projection effects? So that's maybe one question that I have about the comparison, is there a room for more projection of these large scale filament out to beyond gigaparsec regions? Is that properly accounted for so far in the comparison at the moment?
I'm happy to say a few words, but I know Ben has his hand up, so I don't know what the order of operations is.
I think you should go ahead, Colin. We'll come on Ben later.
Okay. Yeah, so we include the so-called two halo term, right, when we do the forward model for these signals. So at least in the context of the halo model picture of large scale structure, we are properly accounting for the projection effects that would arise. For Planck, for example, this is very important because the resolution of Planck isn't so good. With ACT, it's less, it's a smaller effect because the resolution is a lot better, so you really are measuring the stuff associated with the object of interest, but it is still important. I think the contribution from the filaments is a really interesting question. There have been some initial studies with Planck data trying to look at stacks where you look basically at the region between a pair of galaxies oriented in a proper way. And people have looked and found initial sort of like few sigma detections, I think, of the SZ signal from filaments. I think the interpretation is quite tough with Planck because of the resolution. I mean, it's sort of 10 arc-minute resolution in the Compton Y maps. With ACT, we can get almost a factor 10 better in resolution. So I think it's going to be quite interesting, actually, to try similar exercises. Now that we have these wide area multi-frequency maps from ACT, I think this is actually a very interesting question to try to pursue. Yeah.
And Nastasha asked a question, and I think it's directed toward you, Colin. Does the halo model and two halo term underpredict power in power spectra around halo edges? And could that be a similar issue?
Yeah, that's a good point. It's true that the region where the halo model is traditionally least accurate is in this transition regime between the one halo term and the two halo term. Yeah, that's an excellent question. I think the way to check these things is to do comparison to predictions from hydro simulations where everything is included by construction. Yeah, Nick probably has thoughts about this as well.
Yeah, no, I agree with everything Colin just said, as usual. And I'd like to point out, remember, these are CMAS galaxies for this comparison in Amadeo. So they aren't, your run-of-the-mill, like smallish Milky Way size. These are pretty massive, generally the biggest things around. And remember, the thermal SZ drops off like mass to the 5/3. So in order to get sort of a significant contribution in the outskirts or along your line of sight, you have to have like chance alignments with like clusters or massive groups. And that doesn't happen too often, right? And in particular, these are often chosen to be isolated, at least for CMAS. So and as Colin said, when we do the modeling, we do project everything out in the simulations out to very large radii. So if they are in the simulations, they will be there in our comparison. So that's one of the reasons why I'm not too concerned. If we were to push down to, say, Rachel's question and try and do things around 10 to the 11 solar masses, then yes, we have to be extremely careful about projection of, these line of sight projection effects and two halo terms there, because those will be intersecting tons of, at least for the thermal SC, those will be intersecting tons of other halos along the line of sight. So yeah, I'd be more worried there than I would be in sort of these sort of group scale objects that we're looking at with CMAS.
Yeah, for these very low mass things, I think you need something more like CMBHD or at last to really try to attack those questions. Even with something like CMBS4, I think the 2 halo term is, especially for thermal SZ, it's just too big to say something precise about these really low mass objects.
Can you remind me of the time scale of like at last and these new?
Yeah, for at last, that's a good question, Nick. I know CMBHD was kind of proposed as a maybe sort of similar time scale to later time scale after CMBS4, so sometime in the 2030s. At last might be sooner than that, I'm not sure.
So Claudia's on. Claudia can tell us about
great, yeah.
She is the PI.
Yes. So Atlas, the design study will be concluded in the 2024. And at the end of it, we will have a budget, and we will also have the, let's say, the study in place to merge with the Japanese LST project. And at that point, it will be, we will start approaching funding agencies, et cetera, So I don't see construction happening. Tony maybe is more optimistic, but I honestly don't see this happening before 2030. So yeah, that's the. But also there is also like in Europe, unless we get someone from the US to help us with the funding, in Europe the options are limited. So we have, of course, we are looking at ESO, Max Planck, but ESO has a little burden to take off their shoulder before they can fund Atlas, which is the ELT. So they basically, the ESO-DG told us very clearly, like we first need to secure the funding for the ELT before thinking about anything else. So,
will you still have to stack with Atlas, or will you be able to image individual objects?
You can image individual objects. I mean, we.
In terms of signal to noise, when you collect?
Yeah, we expect to be. We expect to be sensitive enough to, now that for the exact numbers, we have to wait until we have a telescope simulator, because right now we are extrapolating also in terms of number of pixels we have, because we are aiming for a 2 degrees field of view. So right now there's not the technology to fill it, but we hope to fill it at some point. And that gives you a lot of, if you manage to fill the entire field of view with detectors, that gives you a lot of signal. Yeah, but the details, like there is some preliminary numbers if you want in the SPIA paper or in the Astro 2020 papers, but the numbers will be more like reliable after the design study.
This may be a little bit offbeat, but while we're waiting for these new capabilities, there are going to be in the nearer term future, although not immediately, sort of next generation radio telescopes, Continuum and H1. And so in week 4, we heard from Mary Putman about, looking at the lack of H1 and other signs of stripping in galaxies around the Milky Way. There may be some potential for doing that around lower mass isolated galaxies as we have ELTs and as we have next generation H1 telescopes. Now, I don't know about those capabilities off the top of my head, so if someone else wants to say something, then they should go ahead. But I think that in lieu of direct measurements, we may be working with indirect measurements for a while.
I think Mary is on the call if she wants to say something about the future radio capabilities.
Okay, Jess. Yeah, the main surveys going on, there's in South Africa, I know less about those, and also the ones, but in Australia, there's the Wallaby survey that's doing the entire southern sky. And I mean, Alfalfa kind of blew apart what we knew about the H1 mass function, et cetera, and the small, well, not small, in the 33% of the sky that Arecibo covered. And so ASCAP will be that much deeper. I don't have the numbers right on my head, but it'll be able to get a LEO T, which is only about 10 to the 5 solar masses of gas as probed by neutral hydrogen, which is going to be the main component, it's just going to take that much further. And I'm sorry, I can't spit out the exact number right now, but it is true in terms of probing content, the low mass galaxies and gas content, and also halo features. It also has this exquisite resolution combined with that, so you'll be able to map a huge suite of galaxies, and so you'll be able to look at what's going on the disk halo interface in terms of that cold gas as well.
Great. So maybe we don't have to wait till 2036 after all. Okay, so I'm going to switch gears to a comment by Ben, actually, who also had his hand up. So maybe he'll enjoy this. But he posted an image that's getting a lot of reactions with Slack emojis, little heart eyes, 7 heart eyes. And Ben wants to urge us to not ignore groups and that kind of intra-group medium in which we still have quite a bit to understand. And so maybe Ben wants to elaborate a little bit on this, and perhaps some of our panelists can chime in as well.
Sure, yeah. Yeah, I've been thinking a lot about groups lately, you know, like M200, M Virial between 10 to the 13 and 14, that intermediate range between clusters and L-star galaxies, and something, you know, related to what we were talking about earlier is how they are, you know, appear to be evacuated of a lot of their baryons, which, you know, is one of the strongest evidence of, you know, for, you know, pretty effective, you know, superwind feedback, probably working at high redshift. So I had my hand up earlier saying that there's nothing to, you know, it should not be surprising that, you know, you can blow a lot of baryons out at high redshift, you know, hundreds of kiloparsecs, which becomes, you know, megaparsecs or a megaparsec or megaparsecs later on, without needing to see, like, you know, these FR2 radio sources. Maybe those are working at high redshift in a way that is surprising. So pushing up, you know, these types of observations of where the baryons are, what they're doing at high redshift, I think is something a lot of us would be interested in, especially in terms of how groups appear today.
I think it's a great, you know, it's a great point. Groups are infinitely more easily observable, at least in some wavebands, than, you know, small halos, and with future capabilities, you can actually observe them at very high redshift. So, you know, for example, for links, we projected that we can do, you know, groups below 10 to the 14 in range of a few times 10 to the 13 at redshifts of 3, you know, and not just detect, you know, it's collect enough signal to measure, you know, thermodynamical properties, structures, and that brings those measurements in terms of mass scale, you know, relatively close to the scale of galaxy formation, and in terms of cosmic epoch, right in the epoch where, you know, the action is going. So, you know, these measurements are very, very important now, and they will be, you know, very important in the future.
I want to echo. I think. Oh, sorry. I was just say we love groups. These are ideal objects for us with SD work. I mean, this is essentially the scale that Nick showed the measurements of already with ACT. We're doing similar measurements with, you know, this projected field KSD estimator in my group at 5-6 sigma significance already with just Planck data. So that's going to increase by a dramatic amount as we fold in ACT data in the next year or two. Yeah, the forecast that we did for the, you know, the Simons Observatory, the CBS4 Astro 2020 reports, you know, indicate that we're expecting signal to noise of probably hundreds on these types of measurements in the next 5 to 10 years. So this is a regime where we really expect transformative measurements to happen. So I'm very happy to hear that people from the simulation and theory side of things are interested in learning from these measurements, because we're going to give you a lot of them. Yeah, so I'm happy to hear this.
Colin, can you just say, like, where, you know, what redshift specifically?
Yeah, we forecasted things out to redshift of 1 for sure. where I think we have a better idea of what the samples available for cross-correlation are going to look like from DESI, for example. We also have these amazing catalogs from photometric surveys, of course, as well. A lot of the forecasting Nick talked about is for spectroscopic surveys, which are a bit cleaner in some ways. But we have these infrared selected catalogs from WISE that contain 500 million galaxies, sort of massive galaxies, low mass groups. And then LSST is obviously going to be a machine for finding this stuff as well. So I think we have a pretty clear picture of what we can expect in these measurements out to Redshift 1. There will certainly also be data out to Redshift of 2. I just think that we have less maybe ab initio idea of how many objects to expect out there and what their properties are going to look like. If they're truly evacuated of gas, for example, then we won't detect as much signal because there will be less signal to detect, but that will still be a very interesting observation, right? If you try to look for gas and you find that there's no gas there, that's already telling you something quite interesting, I think.
But you're sensitive to gas at large radii more so.
That's right. Yeah, that's right.
Gas at other that is missing in other probes.
Yeah, that's right. Yeah, so even with current measurements from Planck, for example, we've now confirmed that the cosmic baryon abundance is present out at several times the virial radius at redshift of 1, for example. So the missing baryons problem in that sense kind of is solved in the sense that we know that they're all there, they're just out at large radius, and then the question is how are they distributed as you go down to smaller radii. So we're definitely going to learn a lot about this in the next 5 to 10 years.
Excellent. And one thing I'm interested in, and maybe Edmund, who I think just had something to say, he flashed his mute button, or Aurora can comment on this. How much then, in that case, do we stand to learn about kind of resolving some of the arguments about the Milky Way halo versus local group medium? Or is that just too out of left field? If you don't want to talk about that, Edmund, you can say what you were going to say otherwise.
I mean, I guess I'd have to think about that a little bit more. But what I was going to say was related to that, which is that I think that it would be a good idea for people to think about like how to combine the metrics that we're going to get out of a survey like ARCIST with what we're going to get out of the SV, because you're going to get complementary information, and something similar like that could be done with the Milky Way to some extent already, because we do have better absorption data for our own galaxy. In terms of resolving whether or not, so as we discussed back in week 4, the Milky Way and Andromeda have not yet had their collision, which means that whatever group medium is there is not like what it would be if you had a fossil group with a big galaxy that had merged and then now it has its surroundings. And the total mass between the two of them is not all that large, so you wouldn't expect the temperature to be especially high. So I think that maybe some of the like the work that Shizei Ku is doing on like the local bridge, I mean, understanding the using SZ and other metrics to understand the current dynamics between the two is going to be pretty interesting for how we interpret data from other galaxies. Whether or not we can really isolate something that is clearly a local group versus something that is, tidal related to the two yet to merge big galaxies, I'm guessing that we will not be able to completely say for sure that there is this more diffuse extended group medium that is absolutely unreal, that was like a precursor to what's already there.
All right. So thank you, Edmund, for clarifying that. Okay, so I'm going to switch now to a comment by Brian OShea. And if he wants to unmute and speak for himself, he's welcome to do that as well. But he's hoping that with CGM dynamics, you could make stacks of galaxies based on orientation, including tilt with respect to the plane of observation, and you could then, in principle, say things about outflows, inflows, in addition to rotation, and so this does sound absolutely tantalizing to me, and Nicholas Battaglia seems to agree. So maybe I can get people to talk a little bit more about the dynamics of the CGM. see. Brian, you're unmuted, but we can't hear if you're talking.
Sorry, I'm having irritating computer problems. Well, you covered my question and the answer, so I think we're good from my end. I am curious to hear what other people have to say about it, though.
Yeah, I just wanted to comment. So I think we haven't, at least I may have missed it if it was earlier, but I don't think we talked about the rotational KSZ effect in too much detail. But yeah, if you have galaxies that are rotating differentially, as we sort of expect to be the case for many objects, you can, build estimators to look for this effect. For example, if you have some IFU data that gives you some map of the velocity structure of the object, then you can do a stack. There have been attempts to look for this so far in data from, I think, just Planck, and we just have upper limits. But we do expect to be able to make detections of this signal in the next, I'd say, few years. And that then tells you about how the gas is actually, rotating within the halo, which is pretty cool. I think people haven't maybe thought too much yet about what we can do with that signal. So that could be an interesting thing for people to think about here.
Yeah, so that was the final bullet. That's what I was referring to in the final bullet of my presentation. But I think what Brian's asking is, in principle, if we have, there's also potential, the galactic fountain, right? So it would depend on how far out this fountain went or these outflows went. In principle, if that was along the line of sight, and we had some tracer in which we could use to orient it, we could try and look for that as well, as opposed to the rotation. And what's kind of nice is if you pick something that you think should correlate, everything else, like the rotation or even the peculiar velocity, should cancel out. It'll just be additional noise to what you're trying to actually observe. So if there are ways, and people have shown that, this particular estimator aligns with, your outflows, then that is something, the KSZ is sensitive to, is your sort of line of sight velocity. So in principle, it could work. In practice, it's probably the devil's in the details, right? But I think that was Brian.
I think we would just need this tracer, right? I don't know if people have ideas for what this would be, but if there's some observational tracer that we could have of these potential outflows, this is a great idea. Yeah.
But I think if you have if you can take like an optical survey and basically estimate which way the galaxy is tilted, right? I mean, if you have a spiral galaxy, disk galaxy, it's disk shaped, right? So if you are looking for something that's tilted along the line of sight, you can basically look at the ellipticity of it and make a very coarse estimate.
And I know Stephanie Ho is here, and I know she's thought a lot about galaxy orientation effects from an observer perspective and simulation perspective. So I don't know if Stephanie wants to say anything, not to put her on the spot. And I don't know if she's in a place where she can say anything. But
I guess I'm just not too familiar with the SE effect, so I'm not sure how at least from my knowledge, how to connect that from the SE effect to magnesium to observation for the cold gas. But combining geometry with signals detected with in other waveband is definitely useful. As in Crystal's talk, she also mentioned how important is geometry in understanding, for example, outflow inflows, as you guys just talked about.
Yeah, I mean, I know that I'm very excited by the prospects of this for sure. Okay, so maybe in our last 4 minutes, I can get some of the panelists or keynote speakers to just talk about ways in which the SZ community and the X-ray community can interact productively to kind of, get a handle on some of these constraints that we're talking about.
So here's a related thought that was going through my head. To answer this question of whether this sort of excess energy or pressure is coming from the inside and sort of being pushed out from the cluster, or whether it's sort of accreting or coming from filaments or the cosmic web, it seems like combining X-ray observations, which mostly probe the central part of the object, with these more extended SC observations should be a really strong constraint on that problem. So of course you can look in simulations, but simulations are expensive. So, I know that this group has been developing this parametric model. And it seems like that might be a really powerful tool to try to combine these two kinds of observations together and answer that question. So that's one way maybe that the two communities can interact, is via a model, which of course helps us to tie those to physical processes and tie them together.
Yeah, I think it's fundamental to realize just how complementary, SZ and X-ray observations are. X-rays fundamentally can image individual objects, resolve structures inside the virial radius. SZ, you have a capability to do huge samples, trace the gas, very far out. These are just different types of observations that we will do eventually, and it is important to be able to do huge samples, and it is important to see what's actually going on. This is a lesson we learned from doing galaxy clusters. When we, back in the day when we modeled axisymmetrical surface brightness profile, we were not learning much. It's when Chandra came online and XMM, and we started really imaging 2D, 3D structures. That's when there was a revolution in understanding galaxy clusters.
Joel, I notice you have your hand up. Maybe you have some thoughts on this too.
So, one can take a look at what might be coming down the road by seeing what has been done on clusters, just to amplify on what Alexey said. There were big efforts that were very successful comparing X-ray emission, SC, weak lensing, and there may have been one or two other things together to understand what the differences were. They weren't that great, so we know things like the gas in clusters isn't highly clumped and giving us misleading information. And one can try to do this with various stacks of nearby objects. And I say nearby because if you're going to get X-ray emission, you have a big advantage of using objects at a Z of 0.01 instead of 1. But that's certainly possible, and it's I think we've done just about as much as we can with current instrumentation. But coming down the line with Athena and in emission with Athena and Hubs, the Chinese project, will give us a lot of information on the extent. Right now, you can take massive nearby spirals, for example, and you can see their X-ray emission. You can extrapolate them out to R200 and compare them to what you expect to see with, what's seen in SC stacks. And right now, there's a very significant discrepancy because I think the SC stacks are mainly weighted toward early type galaxies that live in clusters and are often contaminated by that sort of signal. So I think the future is pretty good, and we can see that from what we did and what was done in clusters.
Great. I like ending on that note. The future is pretty good. All right, it's 1 after the hour here. I just want to thank our keynote speakers again and all of our panelists for a stimulating, I think, productive discussion and very forward-looking. We have tomorrow where we'll come back and do some of the structured discussion work, do deep dives into some of these really interesting questions that have come up. So I'm really looking forward to seeing everybody back here tomorrow. In the meantime, I'm going to post that new workshop photo with our additional, I think, something like 45 people that made it into the photo. And don't forget the social event today at 4:30 on Room. Edgy room. It's going to be so cool. Bring a drink, and thanks so much, everybody, and we'll see you tomorrow.
Thanks, everybody.
Thank you.